chemical reaction, both the theoretical part, also some numerical problems. I try to solve it, and today the last part of this particular lecture, that is on kinetics of homogeneous chemical reactions. Now, if you look at in the previous lecture, what we try to cover, initially we discussed about the rate equations for irreversible reaction, then rate equation for reversible reaction, then rate equations for the chain reactions, and then we try to find out how you can find out the time required for getting the maximum intermediate product concentration, product concentration in chain reaction, or then we try to solve some kind of numerical problems, try to calculate the activation energy of a chemical reaction, then try to analyze some how the time of conversion related, time of reaction, how it is related with the percentage conversion of the substrate. And today what I am going to do, that I am going to discuss a typical type, another special type of reactions, what we call second order reaction, because up till now mostly we covered the first order reaction. So we try to find out that how the second order reaction, the problems of the second order reaction can be solved, and also I have a problems on the chain reaction, and about two different approach how we can use for solving a chain reaction. So first let me go through this problem. That first problem is that this is we quoted from that Helen and Jungers that published in 1957. The presents the data, the table, if you table on the reaction of sulfuric acid and diethyl sulfate in aqueous solution at 22.9 degrees Celsius, and the reaction is this. This is sulfuric acid in presence of diethyl sulfate, it produces the ethyl bisulfate. The initial concentration of H2SO4 and diethyl sulfate are each 5.5 moles per liter. Find the rate equation for this reaction. Now, previously we can remember that we try to solve the first order reaction. We try to develop the rate equation for the first order reaction, and this is the second order reaction we try to solve today. Now, this is the data that is given. This is you can see that with respect to time, how the product concentration that changes, that has been given here. This is all data is given here. Now, this is a reaction, and at time t equal to 0, that Ca will be Ca0, but at time t, that what will happen, that the Xa will be converted. This is not Ta0. This should be at time t. This is not Ta0. This is equal to Ca0 minus Ca0 into Xa. Let us assume the Xa is the conversion. I told you previously also, Xa is the fraction, that the substrate fraction that is converted. This is Ca minus Ca0 minus Ca0. This is like this. So we can, this is the fraction of B that is converted, and this is what that product formation take place. The concentration of product can be expressed as this, the 2 Ca0 into Xa. Xa is the concentration of divided by 2 Ca0, because this is Ca0, this is also the equimolecular is there. So we considered that that Xa, the fraction we can that is Ca that so ethyl bisulfate divided by 2 moles of initial substrate concentration. Now, this is from this we can write this expression, because if we have this value, that is concentration of this divided by 2 Ca0, and Ca0 value is about 5.5. This is given here, and so we can calculate. We can find out the value of Xa, and just we can find out the value of Xa here, and with respect to time, we can find out from the table. Now, this is the correlation that we have, because because this is like this, something like this, A plus B gives 2C, like this. This is the reaction that we have. So this can be presented like this. This is K is the rate constant if you have. Now, what we can write, this is the rate of substrate degradation, A or B, whatever is there. Then this is equal to K into Ca and Cb, and Ca is equal to Ca0 into Ca0 into Xa. This is the fraction that is converted, and that remains. And here also that Xa, the same fraction, equimolecular conversion is there. So we can assume the Ca0 minus Ca, that is there, because Ca0 and equal to Cb0, that as per the problem is concerned. Then we can take the Ca0 common, then if we can have the equation that like this. So we can have this equation that K into Ca0. So here Ca0 and here also Ca0. If you take common, then the Ca0 squared is there. So one Ca0 will cancel. So another Ca0 is remain. So 1 minus Xa square, that is there. We can write this expression like this. Now, once you get this equation, that this, so I can take it in this side, 1 minus Xa, I can take it this side, and dt I can take it this side. So I can write this is that dxa divided by 1 minus Xa square equal to K into Ca0, and then if you do the differentiation, we'll get this equation that Xa by 1 minus Xa K into Ca. So if we plot now, if we plot Xa versus 1 minus Xa versus t, then in this equation, if you see that here, if you plot Xa by 1 minus Xa, if we plot versus t, if we plot, this pass through the origin, and slope will give you the value of K into Ca0. So we know the Ca0 value, so we can find out the value of K. So this is exactly that. From the slope we can find out that value of K we can find out, and this is how the K value is coming around this. Now once we get this K value, then we know our rate equation. What is our rate equation? Minus Ra equal to K into Ca by Cb. Am I right? So now K value has been determined. So we can put this K value here, and this is how we can write the rate equation. And again, I am telling you, if we want to do the validity of the equation, we can easily do by ourselves. In that case, we shall have to find a correlation between the time and the substrate concentration, and you have the theoretical values, theoretical plot, and compare with the experimental plot. From that you can do the validity of the experimental results. Next problem that is also very interesting, that a 10 minutes experimental run shows that 75% liquid reactant is converted to product by half order reaction. So up till now, what we have discussed mostly the single order reaction, or and also we double order reaction, first order and second order reaction we consider. But this is the half order reaction, and what will be the amount converted in 30 minutes. So that we shall have to find out. Now, so in this problem, the 10 minutes, the fraction converted is 0.75, and question is after 30 minutes, how much fraction of A will be converted. Now the equation half order reaction, this if we assume A to B, that if K is the rate constant, I can write that minus Ra equal to K into Ca to the power half. So I can write this as minus Ca by dt. k into Ca to the power half, then we can take it here. Now, this equation, this is differential equation is like, the solving is like this, x to the power n dx equal to x to the power n plus 1 divided by n plus 1. Now, if you do the similar things here, we will get the solution here 2 into Ca to the power half minus Ca0 to the power, because integration is from Ca0 to Ca equal to k into minus k into t. Now, once that here we have this equation, then we at the same time we know that Ca equal to what? Ca equal to Ca0 into 1 minus x a at any point of time. So, in this equation we can put the value of Ca, then we have this equation, and then for different two different time, because the T2 and T1, if the fraction T1 time x a 1 is converted and the time 2 x a 2 is converted, then we can have the expression is like this. Now, this if we put this value of x a 2 as 0.75, then after 30 minutes conversion is 75%. Now, previously we have seen in the problem that also that initial conversion also that also 75%, and I can go back. If you look at now this here what we have done, that the problem was at 10 minutes that conversion is 75%. Now, when we calculated here, we calculated here, then also we find that after 30 minutes the conversion is 75%. So, both cases the conversion is same. Now, we try to find out why this is happening, and then what we have done, we have tried to develop the correlation that we have here, and with respect to this time, that you see that we can write this equation like this and we can solve it, and we will get this equation, and 10 is 0.75, then it is about 20. Am I right? Then if we go further, then 20 equal to t by x a, this one, this is the correlation that we have. Then we can write x a, if we solve it, x a equal to these equations. Now, in this equation, if we put the value of different value of t, then you can find out the x a fraction. So, then we can find a correlation. We can find here, we can find a correlation of this is x a. Am I right? This is x a and this is time. So, if we put this equation, you will find this correlation like this. That means that 10 minutes time, that you 75% conversion, 20 minutes time the 100% conversion, but 30 minutes again, as per the calculation is concerned, it is coming back to 75% as per our equation is concerned. So, this is the typical observation we have, that at 20 minutes, if you put the 20 minutes, the x a will be 1, that in x a will be 1 means 100% conversion of substrate take place. But at 30 minutes we have 75%. So, that is why we try to find out that why this is happening, how this is happening. We try to develop the correlation and establish the fact like this. Now, last problem that I want to discuss today, that is chain reaction, that I have already discussed the theory part of it. This unfortunately this has gone to this side. So, if you look at A to R, R to S, so I can write here A to R, R to S like this. So, this has shifted here. So, it is like this. Now, for the elementary series reaction A to R, R to S, this is C, if is at T equal to 0, Ca equal to Ca0, and R, that is the intermediate substrate concentration, and the final substrate final product for final product concentration, that will be equal to 0. This is the boundary condition. Is that the question is that maximum concentration of R, find the maximum concentration and when it is reached at T max, when K1 equal to K2. Now, previously we did not assume the K1 equal to K2, we assume that K1 and K2 they are different when you develop the correlation. Now, this particular problem deals with that what will happen when K1 is equal to K2. So, we use two different approaches to solve this problem. Now, first we have this we know that this equation we can write for rate of degradation of RA. The A it can be written K1, this will be K1 and K1 into Ca, and R equal to K1 into Ca. This will be K1 and this is K2, not coming properly. So, I can write like this, that RR equal to K1 into Ca minus K2 into Cr. This is unfortunately it is not come here. So, and rate of formation of R, that R S will be what? S will be equal to K2 into Cv. This is we have seen before also. This is how it can be expressed. Now, the reason it has been written that K1 equal to K2. So, we finally it looks like this. Final equation, if you look at it, looks like this, because the reason is that K1 equal to K2 equal to K. If we assume that, then the equation will come like this. Then we can write the overload reaction like this. Now, we have already seen that that total initial substrate concentration at any point of time is equal to Ca plus Cr plus Cs, because if we assume this is equimolecular conversion. Now, if you look at the first that substrate degradation, that is equal to how you can write dCA by dt equal to K into Ca. Am I right? So, we can put it here, so minus dCA by Ca equal to K into dt. So, this is equal to dln Ca. So, this I can put, this is minus K into dt. So, if you put Ca0 into Ca and this is 0 to t, then we can write that ln Ca by Ca0 is the minus, this minus I can take it here and into minus Kt. So, Ca equal to Ca0 into e to the power minus Kt. Now, in the second part of the reaction, because if you look at, this is like this, A to R, R to S, am I right? So, this is K and this is K. So, rate of formation of R will be what? K into Ca minus K into Cr. So, now I can take this K at this side. So, this is how it has come, that dCr by dt plus K into Cr equal to, now this we have already find out, Ca equal to what? Ca equal to Ca0 e to the power minus Kt. So, I can write this expression like this. So, if we multiplied both sides by e to the power k, both sides if we have multiplied, then e to the power minus kt and minus e to the power plus kt, they will cancel each other and we will be having k Ca0. Now, this is equal to nothing but dCr by e to the power kt by dt equal to k into Ca0. Now, then we can write that dCr by e to the power kt equal to what? Equal to Ca0 t into dt. Now, this can be written in this form, Cr into e to the power kt equal to k Ca0 into t plus constant. Now, applying the initial condition or boundary conditions at t equal to 0, r equal to r0 equal to 0. So, constant will be 0, because if t equal to 0, then this also will be Cr equal to 0. So, constant also will be equal to 0. So, this equation will be what? Cr into k into Ca0 into t. So, Cr, if you write the expression for Cr, then e to the power kt, that will come this side. So, if you can write k into Ca0 e to the power minus kt into t, this is the final expression that we have. Now, we have already seen what we have seen, that Cr, when we plot Cr versus t, what kind of plot we have? It is increases then decreases. Am I right? This is like the kind of plot we have. Now, at T max, this is equal to T max. At T max, this will be Cr max. So, at this particular situation, what will happen? d Cr by dt, that should be equal to 0, what we have written here. As Cr max, say d Cr by dt equal to 0 when t equal to T max. Now, if you put these conditions that in the previous equation, so this equation, now if you differentiate this, that then what will happen? D Cr, but here you see that we have these two variables we have. We have here e to the power minus kt and with over t. So, we can differentiate. If you differentiate here, what will be there? Cr by dt equal to k Ca0. You can take common actually. Then we can differentiate first with respect to this will be minus k into e to the power kt into t. Then minus, we can write e to the power minus kt into 1, because t differentiation with respect to 1 is 1. So, this exactly this we can show it here. Here, if we differentiate that, we will get this minus will be plus, that we will get this equation like this, e to the power k1 t equal to kt. This is equal to this one. That then what we can do, that this cannot be equal to 0. Am I right? This cannot be equal to 0. So, if it is not equal to 0, I can assume this is equal to 0, and if you put this equal to 0, then T max will be what? T max equal to 1 by k, because this will cancel. Am I right? This will cancel. So, your kt will be equal to 1, and if your kt equal to 1, then I can write t equal to 1 by k. This we can write, and this t equal to T max. Now, this T max value you can put in the previous equation. We had the previous equation is there. So, we can put the previous equation. You put the T max equal to 1 by k, and if we 1 by k, this k will cancel with each other. Then if we cancel, then what will happen? That we will be having this will be Ca0 into e to the power minus 1. Am I right? If it is cancelled, it will be minus 1, and if it is minus 1, we can write in this form, the Cr max equal to Ca0 into E. This is one approach, this easy approach, simple approach, logical approach through which we can solve this problem. There is another approach that also we have. Now, we shall have to go back to our early derived equation, that where we have shown that T max equal to ln k2 by k1, k2 minus k1. Now, here if we put k1, this is valid when k1 not equal to k2. Now, when k1 is equal to k2, then what is happening, that this will be 0, and this also the log 1 equal to 0, and k minus k equal to 0. So, it is undefined, 0 by 0 is undefined. Now, here if you put the limit, that limit k tends to k2, k1 tends to k2 T max, then limit will be this limit ln k1 tends to k2 ln k2 by k1 k2 minus k1, then this is not equal to exactly 0. Then if we then we can write k2 minus k1 equal to x, this we can write k2 minus k1 equal to x. So, k2 will be equal to x k1 1 plus k1 plus x. Then I can modify the equation like this. Then then if we put the the hospital rule equation is like this. If you limit x tends to 0, x ln x limit, this will be like this. So, we can write in this form. The same form we can apply it here. We can come in this form, and if we apply this form, then we will find that this is will cancel. Then k1 will cancel. This will be 1 by k1, and then x tends to 0. I can ignore x. Then it will be 1 minus k1, and then since k1 equal to k2, I can write 1 by k2 equal to 1 by k. Now, second approach that we have, again we shall have to go back to our early that what we have derived. Then in this we have shown you that CR0 by CA0 equal to this. Now, here also if we put k1 equal to k2, then this will be 1, and this is 1 minus 0, 1 minus 0 equal to infinity. This is undefined. What you call is the indeterminate form. Now, this equation also we have seen this is undefined. This way also we can find this is undefined. Now, if you put the limit that this is k1 tends to k2, we have this equation like this. Then this let us see how we can solve it. Then again we can assume k2 minus k1 equal to x, k2 equal to k1 plus x. Then we can write this equation in this form, and then if we solve applying this law hospital rule, then we will get this is equal to minus 1. Then if this is equal to minus 1, then this is like this. Then CR by C max CA0 equal to CA0 equal to this ln is there. So, ln I can ln, if we take it ln out, that is CR max by CA0 equal to e to the power minus E1, and CR max equal to CA0 by E. So, this is how we can solve this equation in other approach, but I feel that the first approach might be comparatively easier as compared to the second approach. So, what I want to conclude this homogeneous reaction kinetics, because here we try to find out the different equations for different type of reactions, both irreversible reaction also of different types, that we have simple A to B reactions, we have parallel reaction, we have autocatalytic reaction, and we have also the chain reaction. And another reaction we have the reversible reactions. So, we try to derive the rate constant as well as the order of reaction of this particular reactions, and to establish the rate equation. We try to justify when you write any kind of rate equations, we shall have to do the validation of the experimental results, and to validate the experimental results, we shall have to find a correlation between time versus substrate concentration, and then we can compare with the experimental results, and if a deviation is less than 5%, then it is acceptable. If more than 5%, we shall have to modify this equation. So, we try to solve different equations. I hope the conception on the reaction kinetics will be little bit clear to you. Thank you very much.